At 10,000 feet above the Pacific, the release lever on a Nakajima B5N2 Kate tripped, and gravity claimed a single object. This was not a standard aerial munition. It was an armor-piercing weapon repurposed for a new kind of vertical warfare. U.S. sources commonly identify it as the Type 99 No. 80 Mark V armor-piercing bomb. It was a thick-walled, hardened steel body built to survive impact and drive deep before its delayed fuse functioned. Accounts often describe it as derived from very large caliber naval shell design practice, but the exact parent shell is not consistently documented in public sources. Engineers adapted the hardened body for aerial release and fitted stabilizing fins to keep it true in a near vertical fall. The result was a kinetic hammer weighing 1,760 pounds. It did not rely on a massive explosive charge to destroy a target from the outside. It relied on mass, velocity, and a delay fuse to destroy a target from the inside. As the weapon accelerated toward the harbor, it built up sufficient kinetic energy to defeat horizontal protection, the core premise of armor-piercing physics. A standard high-explosive bomb detonates on contact with the superstructure, shredding antennas and unarmored steel while leaving the ship's vital spaces largely intact. This converted shell was built for the opposite outcome, to stay rigid at impact and keep going. It wasn't designed to stop at the deck. It was meant to punch through the weather deck, break the armored deck below, and carry a delayed ignition into the ship's core, destroying from the inside, not bursting on contact. Then it met its target. The projectile struck the USS Arizona forward on the starboard side in the vicinity of Turret 2. It punched through the upper decks with a violence that surviving eyewitnesses struggled to describe. Exactly which compartments it traversed is not recorded with one single, universally agreed map, but the outcome is clear. The bomb's penetration was followed almost immediately by a catastrophic explosion in the ship's forward powder spaces. What doomed the vessel was the convergence of penetration, confinement, and stored propellants. Accounts differ on the exact room the bomb reached. Some point to a black powder space used for salutes and auxiliary charges, others to smokeless powder stowage. But the chain is consistent. A fast-building fire and pressure event inside sealed steel, breaching boundaries and cascading into the forward magazines. Inside the main magazines, tons of smokeless powder lay stacked in silk bags. Smokeless powder is a propellant, not a high explosive. It is designed to burn in a controlled manner to push a shell out of a gun barrel. However, when containment is breached and it is subjected to the intense heat and pressure of a black powder deflagration, the burn rate accelerates exponentially. The propellant inventory did not just catch fire, it transitioned into a massive, expanding gas event that the hull structure could not contain. Witnesses described a brief, terrifying pause between the bomb's strike and the ship's catastrophic failure. In those few seconds, internal pressure and flame raced through the confined spaces faster than the structure could vent or yield safely. Then the violence found its exit. The explosion tore through the forward deck, obliterating the forecastle. The violence of the event destroyed the forward structure's ability to carry load. Key framing and deck supports failed. With their foundations compromised, the heavy armored turrets dropped into the void the blast had opened. In less than a minute, the Arizona was no longer a fighting unit. She was a broken mass of steel settling into the harbor mud. For the salvage engineers watching from the shore, the smoke column marked the beginning of a new problem. The Navy had just lost a capital ship, and the harbor had become an obstacle course of twisted steel, fire, and leaking oil. The urgent goals were practical: assess hazards, recover what could be recovered, and cut away anything that threatened navigation or further damage. They did not yet know every detail of what had failed inside the hull. They only knew they had to enter the wreck and map the destruction by hand. The forward gun turrets of the Pennsylvania-class battleships were designed to be immovable objects. Each housing weighed hundreds of tons, anchoring 3 14-inch guns into the barbette structure deep within the hull. Yet, when the smoke cleared on the morning of December 7th, these massive steel fortresses had vanished from their original horizon lines. They hadn't been thrown skyward in some outward burst. The ship's forward strength had failed, and the turrets simply dropped straight down into the space the blast had carved out. The entire forward structure of the ship had lost its tensile cohesion, causing the turrets to drop nearly 20 feet vertically into the hollowed-out crater of the bow. That straight-down drop, nearly 20 feet into the bow's hollowed crater, became the clearest forensic signature of what had happened inside the ship. To understand how a 30,000-ton vessel breaks in half in seconds, one must understand the distinction between deflagration and detonation. These two terms describe how energy moves through a reactive material. In a fire or deflagration, the combustion wave moves through the fuel at subsonic speeds. It is a rapid burning process. Smokeless powder, the primary propellant for the ship's heavy guns, is engineered to deflagrate. It is designed to push a shell out of a barrel with progressive pressure, not to shatter the steel breeches. Under normal conditions, a pile of smokeless powder ignited in an open field would burn fiercely, but would not generate a shattering shockwave. Detonation is different. The reaction front runs supersonic and drives a shockwave through material. What happened in Arizona's forward magazines wasn't a clean textbook detonation train, but confinement made it feel like one. As pressure rose inside sealed compartments, burning propellant accelerated into a violent overpressure event. What followed is better described as a cascading magazine catastrophe rather than a textbook detonation train. Smokeless powder was never meant to shatter steel. It was meant to burn and drive guns. But under confinement, with boundaries failing and pressure rising, burning propellant can accelerate into a violent, destructive overpressure event. In a sealed compartment, flame and expanding gas do not simply burn away. They drive bulkheads apart and spread the disaster into adjacent spaces. The result was an overpressure event that the ship's structure could not survive. The blast expanded, vented, and then the weakened forward spaces collapsed. Gravity took over. The forecastle deck folded downward like a hinge, and the massive turrets plummeted into the hull. The human cost of this physics failure was absolute. 1,177 sailors and Marines were lost, most of them instantly. The blast wave moving through the passageways traveled faster than the nerve impulses required to register pain. For the salvage teams arriving later, this number defined the operation. The Arizona was not just a wreck, she was a densely populated cemetery. Every decision to cut steel or pump water would have to be weighed against the presence of the crew entombed within the twisted metal. The damage report classified the hull status as unknown, but the visual evidence was grim. The ship had settled onto the bottom of the harbor, her superstructure burning furiously above the waterline. The water depth was about 40 feet, meaning the upper works were accessible, but the wound in the hull lay buried in mud and darkness. The Navy engineers faced a critical question. Was the keel intact enough to support a refloat, or was the spine of the ship severed? They could not determine this from the surface. The only way to learn what the hull had become was to put divers inside the wreck and let their hands and instruments trace the damage in the dark. To sever steel beneath the surface of the harbor, the salvage teams relied on oxygen-fueled cutting methods adapted for diving work. Period accounts describe divers using tools such as oxygen-carbon arc cutting and oxy-hydrogen torches to slice through wreckage where saws and hammers were useless. In the black water, the technology mattered less than the reality. Every cut had to be made by feel, under pressure, with the wreck itself fighting back. Mastering this tool was the primary requirement for the divers assigned to the Arizona. The initial objective was not to raise the hull, but to clear the navigation channel. The upper works of the battleship, the tripod masts, the directors, and the splintered platforms, protruded into the shipping lanes. They had to be surgically removed. The environment for this operation was hostile to human physiology. The harbor water was a thick, opaque emulsion of mud, debris, and heavy fuel oil. The oil coated everything. Divers descended into zero visibility, working by touch along jagged steel and torn bulkheads. In the years that followed, the persistent seep of oil from the wreck would earn its own grim name, the Black Tears, as dark droplets rose to the surface long after the attack. The psychological strain was compounded by the contents of the water. The wreck was a fresh tomb. The divers were swimming through compartments filled with decomposition and unexploded ordnance. Yet the engineering imperative required them to treat the site as an industrial demolition zone. The first major target was the foremast. The structure had been damaged and leaned precariously. To remove it, salvage crews cut and dismantled major members and attachments, then used cranes to control the mast's movement as it came down onto the wreck. Once it was lowered, it could be sectioned into smaller pieces and lifted away, reducing hazards above the waterline. The main mast posed a different challenge. It was largely intact but anchored deep within the ship. The divers had to cut away the surrounding deck plating to expose the base of the legs. Working in the blind, toxic dark, they sliced through inches of structural steel, careful not to ignite pockets of trapped gas that could cause a secondary underwater explosion. Once the legs were severed, surface cranes latched onto the structure. The steel groaned as the tension increased, fighting the suction of the mud and the weight of the assembly. Finally, the mainmast broke free and was lifted onto a barge, removing tons of top weight from the hull. Through 1942 and into 1943, the silhouette of the Arizona was steadily stripped down. Major sections of superstructure were removed and scrapped for the war effort, and hazards to navigation were reduced. However, the most valuable assets remained submerged. The 4 massive gun turrets, housing the 14-inch main battery, were still attached to the ship. The 2 aft turrets were more accessible, but the 2 forward turrets were trapped in the tangled wreckage of the bow. The engineers now turned their attention to heavy lift decisions. How much could be removed without tearing the wreck apart? The engineering challenge of the Arizona now shifted from demolition to heavy lifting. Removing a gun turret from a battleship is not a simple matter of attaching a hook and pulling. Each turret is a rotatable fortress weighing hundreds of tons, seated on a circular track of precision-machined rollers. To lift one requires a floating crane of immense capacity. However, introducing a heavy load to a floating platform triggers a dangerous mechanism known as metacentric height. Metacentric height is the metric that determines whether a vessel will return to an upright position after tilting or if it will continue to roll over and capsize. When a floating crane lifts a load from the deck of a sunken ship, the physics of the system changes instantly. As soon as the weight leaves the deck and hangs from the crane's boom, the center of gravity of the crane barge effectively shoots upward to the tip of the boom. If this new center of gravity rises above the metacenter, the theoretical pivot point of the hull's stability, the barge loses its ability to right itself. It becomes top-heavy and will flip over, likely killing the salvage crew and dropping the load back onto the wreck. The salvage masters had to calculate this margin of error precisely. They began with the aft turrets, numbers 3 and 4. These structures were outside the blast zone of the magazine explosion. Their roller paths were intact, and their steel geometry was undeformed. The team stripped the armor plate from the turret roofs to reduce weight. Then, using heavy barge cranes, they carefully hoisted the massive gun houses out of their barbettes. These assemblies were transported ashore for planned coastal defense batteries. Battery Pennsylvania was completed late in the war and was test-fired on VJ Day. Battery Arizona was begun, but the project was suspended before it was fully finished. The forward turrets, however, presented a starkly different physical reality. The magazine explosion had dropped turrets 1 and 2 roughly 20 feet into the hull. This vertical displacement destroyed the delicate interface between the turret and the ship. The roller bearings were crushed, the barbette steel was warped, and the structures were effectively welded into the wreckage by the force of the blast. When the divers inspected these forward turrets, they found the metal twisted into locking shapes. The lifting barges applied tension, but the friction and the mechanical interlocking of the torn steel were greater than the buoyancy of the cranes. To force the lift would risk snapping the crane cables or inducing a catastrophic stability failure in the lifting barges. The engineers faced a hard constraint. The cost of extracting these jammed structures exceeded the value of the steel they contained. A compromise was executed. The 3 14-inch guns of Turret 2 were removed individually. The barrels were cut free, straightened in a machine shop, and eventually relined for service on the USS Nevada. But the armored houses of Turrets 1 and 2 were abandoned. They remain on the ship to this day, submerged monuments to the force that broke the hull. With the upper works gone and the salvageable armament removed, the Arizona sat low in the water, a stripped giant. The salvage operation had recovered valuable ordnance and machinery. Now another question remained. What had actually happened to the hull structure below the mudline? The answer could not be read from the surface. Divers would have to clear mud away from key areas and examine the wreck's plating and framing directly to understand what was still sound and what was beyond saving. By 1943, the miracle of the Pearl Harbor salvage effort was visible to the naked eye. The battleships West Virginia, California, and Nevada had all been raised from the mud, patched, and sent to the mainland for modernization. The salvage teams had defied the Japanese assessment that the fleet was permanently destroyed. Naturally, the Navy Command turned its eyes toward the Arizona. The sentimental value of raising the ship was immense, but in engineering, sentiment is a liability. The decision to lift a 30,000-ton vessel rests entirely on the physics of the hull materials, specifically a property known as tensile strength. Tensile strength is the measure of a material's ability to withstand being pulled apart. When a submerged ship is pumped out to gain buoyancy, the forces acting on the steel hull are extreme. The water pressure pushes up from below, while the weight of the armor and machinery pushes down. The steel plating must possess high tensile strength to keep the ship from tearing itself into pieces during the ascent. However, the Arizona had been subjected to a unique trauma. The fires from the magazine explosion and the burning oil had raged for days, turning the forward hull into a furnace. When structural steel is heated beyond a critical temperature and then cools uncontrolled, its crystalline structure changes, it loses its temper, it becomes brittle. The salvage engineers feared that the metal of the Arizona had lost the tensile strength required to survive a refloat. To confirm this hypothesis, the salvage teams had to inspect the one part of the ship that no one could see, the keel. The keel is the spine of the ship, the central beam that supports the ribs and the hull plating. If the keel is broken, the ship is not a vessel, it is two separate piles of scrap metal. The divers undertook some of the most claustrophobic work of the entire project. Using high-pressure excavating nozzles, they cleared compacted mud from sections of the hull and advanced along the wreck by reference points, frames, seams, rivet lines, building a tactile map of damage that no light could reveal. What those surveys confirmed was stark. The central portions of the ship had been catastrophically damaged, and key areas were buried and distorted in ways that made a full recovery effort unrealistic under wartime constraints. Those findings forced a cold calculation. The Arizona was, in practical terms, a total loss. Salvage effort focused on what could be removed safely and usefully, not on restoring the ship to service. In wartime, steel, dry dock time, and skilled labor were strategic resources. Every ton and every hour spent on an irrecoverable hull was a ton and an hour not spent putting new ships to sea. The decision was made to end any notion of major recovery and to leave the wreck in place. The Arizona was no longer a ship to be rebuilt. She was a war grave. The salvage engineers departed Pearl Harbor in 1943, but they left behind something that never stopped working. Deep in the bunkers, heavy fuel oil remained trapped behind riveted bulkheads, some of it still sealed in tanks weakened by corrosion. Over the decades, the hull has continued to weep. Dark droplets survivors and visitors call the black tears, an environmental shadow that proves the wreck is not inert, but a decaying industrial container. While the hull lay dormant, the assets stripped from her decks went back to war. Most striking were Turret 2's main battery barrels, salvaged, straightened, and relined, destined for a second life aboard the USS Nevada. The Nevada herself was a survivor of the harbor floor, having been raised and modernized after the attack. In a grim closure of the tactical loop, the guns of the Arizona, mounted on the deck of the Nevada, unleashed high-explosive salvos against Japanese positions at Iwo Jima and Okinawa. The steel that had been sunk by the Imperial Navy in 1941 returned to destroy Imperial fortifications in 1945. The decision to leave the hull on the bottom created a unique category of war grave. Most of the crew went down with their ship, and the collapsed forecastle made recovery too hazardous to justify. The mud and the twisted steel of the collapsed forecastle made recovery operations too hazardous to justify. In the years following the war, the Navy formalized this reality. The ship was not just a constructive total loss, it was a permanent sanctuary. Survivors of the attack who passed away decades later have, in a number of cases, chosen to have their ashes interred within the barbettes, an official practice that allows them at last to rejoin their shipmates on watch. Today, the engineering reality of the Arizona is a race against entropy. The steel hull is corroding. The structural integrity that was compromised by the bomb and the black powder explosion is now being attacked by the chemistry of the ocean. The overhead structure that supports the memorial building does not touch the ship. It bridges over it, respecting the fragility of the wreck. Engineers continue to monitor the oil leaks and the stability of the bulkheads, using non-invasive sensors to map the rate of decay without disturbing the site. The salvage of the USS Arizona was defined as much by restraint as by action. The engineers chose not to raise her, not to chase a cosmetic refloat, and not to disturb the crew's resting place for the sake of appearances. Instead, they applied cold, rational logic to a scene of total devastation. They stripped what could be used to win the war, and they abandoned what could not be saved. In doing so, they inadvertently preserved the most powerful evidence of the attack. The broken hull remains the ultimate proof of the lethal physics that arrived out of the clear blue sky on December 7th, a steel monument to the moment the world changed.